Welcome to Lee's Science Academy, a study room where you don't just memorize, but understand systematically and logically through the whole picture. This channel delivers basic knowledge of natural sciences logically and systematically, which is good to have before starting your major studies in college. Of course, it also systematically delivers the mathematics necessary for studying science. It is not a lecture focused on simple memorization, but in short, a channel for studying. Of course, it will also satisfy the intellectual curiosity of the general public who want to systematically understand natural and biological phenomena. In the last lecture, we studied the commutative law, among the 3 representative operation rules applied to the 4 basic operations of natural numbers. Today, we will continue by studying the associative law. We will cover the distributive law and the order of operations in the next video. The general definition of the associative law is that, in a given set of numbers for an operation, when performing a given operation on any 3 elements, if the result of calculating the first 2 elements first and the result of calculating the last 2 elements first are equal to each other, the associative law is said to hold for that operation. Did you understand the associative law well? The commutative law was a rule that the result is the same even if you change the order of the terms in a binary operation of A and B, right? The associative law is a rule that in 2 binary operations among A, B, and C, the result is the same even if you change the order of the binary operations. It changes the order of the operations themselves, not the order of the terms. In performing the 4 basic operations of natural numbers within the set of natural numbers, addition and multiplication satisfy the associative law, and subtraction and division do not. I will prove this now. I will prove the non-establishment of subtraction and division by showing counterexamples, and verify the establishment of addition and multiplication inductively. I will show counterexamples for subtraction and addition within the closed range. The associative law requires 3 numbers by definition. As a counterexample for subtraction, we set the 3 numbers for the operation as 19, 8, and 3, which results in a closed operation. Calculating the first 2 numbers first gives an operation value of 8, and calculating the last 2 numbers first gives an operation value of 14, which are different from each other. Therefore, the associative law does not hold. For the counterexample of division, we will set the 3 numbers as 16, 4, and 2 to ensure a closed operation. Since the results of the front operation and the back operation are 2 and 8, which are different, the associative law does not hold. Let's look at inductive examples for addition and multiplication where it holds. When adding 3, 4, and 5, the result of adding 3 and 4 first and then 5, and the result of adding 4 and 5 first and then 3 are both 12, so the associative law holds by the law of identity. For multiplication, the result of multiplying 3 and 4 first and the result of multiplying 4 and 5 first are both 60, so the associative law holds. We can show that the associative law holds for any 3 numbers, but we cannot completely deny the possibility that an instance where the associative law does not hold might be discovered somewhere, someday. So from now on, to eliminate any doubt, I will deductively prove that the associative law of addition and multiplication holds. I will directly prove that the associative law holds for the addition of natural numbers. Let's set the universal set where the operation takes place, U, as the set of natural numbers. Since the associative law requires 3 numbers, we choose arbitrary numbers A, B, and C. These three numbers are naturally elements of the set of natural numbers. As we did last time, we will rewrite the three numbers in the form of addition of ones. A is 1 added A times. B is the sum of B1s. C is added C times. Then the proposition we need to prove is that the result of adding the first two numbers first, A plus B plus C, and the result of adding the last two numbers first, A plus B plus C, are equal. Therefore, showing that the results are equal proves it. I will prove it now. First, on the left side, we rewrite the A plus B that is added first as the sum of ones. Then we add C, and C is also rewritten as the sum of ones. If we let A plus B be P, it becomes 1 added P times. By adding C1s to this, the final operation value becomes P plus C equals D. The total number of ones added becomes D. You understand, right? We apply the same method to the right side, A plus B plus C. First, we rewrite the B plus C to be calculated first as the sum of ones. If the total number of ones is Q, then B plus C equals Q. To this we additionally add A as the sum of ones. Then the final operation value becomes 1 added Q plus A equals E times. However, since the three numbers used are the same total number of ones, the result of the left side and the result of the right side are equal, so D equals E. Therefore, we conclude the proof. Did you understand well? Let's express the addition differently to make it intuitively recognizable. We express the three numbers to be added as the sum of ones, but vertically. A is 1 added A times. B is 1 added B times, and C is added C times. Then, in the operation of doing A plus B first, the number of ones is P. Adding c to this, the total number of ones is d. This time, in the operation of doing b plus c first, the number of ones added is q. Adding a to this, the total number is e. However, since the number of ones represented by d and e are equal, d equals e, concluding the proof. You understood well, right? Then, this time, I will directly prove the associative law of multiplication in natural number operations. As we did before, let's set the universal set of operations, U, as the set of natural numbers, and choose arbitrary natural numbers a, b, and c. Then the equation we need to prove becomes a times b times c equals a times b times c. For the proof, we express the three natural numbers as the sum of ones, but this time we omit the plus sign and represent them using component notation. Then a, b, and c can be expressed like this. In the left side, a times b is represented as repeatedly adding a, b times, according to the definition of multiplication. Then one chunk of adding ones is created. Multiplying c to this means repeatedly adding this chunk c times. Then the operation value becomes the total sum of all ones. You understood, right? Here we will adjust the adding method. First, we create a group that adds components in the same position from each chunk. Then the number of ones in one group becomes b. And if we gather all the numbers of the first component group from each chunk, it becomes c. The number of the second component also becomes c. If we continue making groups in the same way, the number of the last component group also becomes C. If we represent this structure as an operation, first, since there are C groups with B ones, it can be represented as B times C. Also, since there are A of these gathered, it is the same as repeatedly adding the whole, so it can be represented as B times C times A. This expression is equal to the right side. Therefore, since the left side and the right side are equal, we conclude the proof. What are the advantages of utilizing the associative law of operations in actual calculations? For an operation that satisfies the associative law even if there are multiple terms in an equation, calculating the later terms first does not change the operation value, so you are not restricted by the order in which the terms are written and can freely choose the order of calculation. In the actual calculation of natural number addition, even when adding many numbers, you can freely determine the terms to calculate regardless of the written order for convenience. In the calculation to find 55 by adding 1 to 10, you can freely decide the order of addition. As one method, calculating as 1 plus, 2 plus 3, plus 4 plus, 5 plus 6, plus 7 plus 8 plus, 9 plus 10 is possible because the associative law holds. If we apply the commutative law learned last time together, we can even change the order of the terms to be added. By doing 1 plus 9, 2 plus 8, 3 plus 7, 4 plus 6 to get 40, and adding the remaining number 15, we can easily and quickly find 55. If the commutative and associative laws hold, in actual calculations, you only need to calculate the numbers once regardless of the order. Natural number multiplication also satisfies the commutative and associative laws, so in actual calculations, you can multiply any number in the equation as needed regardless of the written order. Because natural number addition and multiplication satisfy both the commutative and associative laws, we don't have to worry about the order in which we write the numbers or the order in which we calculate them when adding and multiplying. You understand that we calculate very comfortably, right? So far, we have looked at how in the four basic operations of natural numbers, addition and multiplication satisfy the associative law, and by applying the commutative law together, you can freely determine the calculation order regardless of the order written in the equation. We also directly prove the associative law deductively. Furthermore, we proved by counterexample that subtraction and division do not satisfy the associative law. Next time, we will study the distributive law as the third rule of operations on natural numbers. We will also look at the order of operations. This concludes today's lecture. Thank you.